Hello. We're here to talk about DDC between three companies, Drivenets, Space, and Credo. I got pulled into this recently, so I am not Ron Almog. I am Peter Cuccinell, and we have two other folks, Kai and Don, maybe. Okay. Oh, here's Don.
Don's not here either.
Oh, okay.
I can do it.
All right, cool. All right, so we're winging it. Okay. So I represent Drivenets. We are the software overlay for constructing this DDC. And the DDC is actually viewed as a way to build networks like cloud infrastructure. Cloud has been using things like storage as a common pool of resource for a long time. Why not apply that to networking? So we see it as we can build DDC infrastructure and include all the network functions, things even down to Ethernet switching as a resource, as a pool that you would use to build and expand on as you need it. Right? So instead of having a single chassis that you're sort of fixed into with the DDC infrastructure, you can scale that horizontally. As well as being able to scale, you can also achieve extra functions like you don't need a single hardware box for just peering or another for routing or another for switching. You can include all those functions in your distributed architecture and have switching components, have routing components, have peering, include third-party services like firewalls and telemetry and other functions like that on top of it. Okay, because we're addressing networking like cloud, we're able to use common building blocks. So with our partners, we can use their physical infrastructure to scale this out. So you don't have an assortment of different pieces of hardware, different SKUs you need to manage. You can use these common blocks to actually build out your fabric as well as your packet processing components. So it allows you to basically focus on what you want out of your network and the teams that you need to support, as opposed to focusing on buying specific equipment to do one specific function. Okay. And another big part about building a DDC infrastructure like this is that we've proven out with our customers that this is a lot easier to implement. So when you're in a data center, when you're doing production work, you can basically deploy this in a much faster model because you don't have to manage all these different separate components, as well as the ability to scale it. So if you want to add an extra 4 terabits, another 8, 12, you just add the additional white boxes to it, and we'll recognize those devices because we're using common protocols to be able to pull those into the DDC architecture. And that way you can scale. I mean, we have proven out we can get up to 700 terabits right now in an infrastructure. Okay, I think that's it for me. All right, thank you. Yep.
Thank you, Peter. My name is Kai Lee. I'm with Space here in San Jose. We are headquartered in Taiwan. We are a hardware company. So let's talk about the building block. Peter just covered all the architecture from a software perspective. We are the hardware side of the business who bring in all the building block. So what we're looking at here is the previous generation, the existing generation, and then the future generation. For the majority of this is based on the Broadcom DNX architecture for the telco side. You can also use these for the mega scale data center. So what we are showing here, as the name imply, DDC, distributed disaggregated chassis. So what we are doing is we are breaking down a traditional chassis by function. And then with the route processor, individual line card, as well as the different backplane. And then we make them into specifically 2RU pizza box. Why are we doing this? Number one is fun. Number two is really for the main reason is for scalability. It's a pay-as-you-go model. You basically got the switching fabric, which I'll talk about in a second, and then you bring in the particular line card. So you don't get into a situation with a big chassis with one line card and you have to pay for a huge power supply, that kind of things. So what we are showing on the top here, way on the top, it's based on the Broadcom Ramon chipset. For those of you who are familiar with the DNX architecture from Broadcom, Ramon is basically the switching fabric doing Broadcom cell switching. They don't understand Ethernet. It's doing cell switching. And all the line card on the second tier, those are based on the Jericho family. Those are doing Ethernet switching, 1500 byte all the way up to 9K jumbo frame. So what we are showing here is 3 generations, starting with the original J2, the Jericho 2, which is switching at 4.8 terabit per second. Then moving forward, right now at this show, we are showing the next generation that is shipping right now with the J2C Plus. That one scale up to 7.2, and we are bringing in 2 chip, a dual chip design with 14.4 terabit. So what we are showing here in one individual pizza box with 2 RU, we can support non-blocking up to 36 port of 400 gig with QSFP-DD. And then the next generation, as Broadcom advanced to the next one, then we will move into the 800 gig and all these other things. It's one thing interesting to talk about is we mentioned about the packet to cell to packet switching. Now, why are we doing that? If you believe all the math and all the scientists and all this white paper, if you are doing switching on the backplane using cell and not fixed Ethernet size, the switching efficiency is actually a lot higher. So take my word for it. There's a lot of white paper on the internet. You can read about it. So it's Ethernet to cell switching and then to Ethernet. One last thing I want to talk about on this building block. When we came to OCP in 2019 and 2020, we talked about the original J2, and that is a 16 nanometer technology. What we are bringing to the show today is the J2C Plus. That is a much more advanced 7 nanometer. Now, what does that mean to you as an end user? As the nanometer gap on these wafer is getting smaller and smaller, 2 things happen. Number one, we can fit a lot more gates into the wafer, meaning to you, with the same size of the chip, you can get a lot more processing power because we can further integrate from 16 nanometer of J2 to 7 nanometer of J2C Plus. And then Broadcom at some point will announce that next generation is reasonable. You can expect the number to continue to come down. So we can dense a lot more gate into the wafer. And the second thing that is really important to you as an end user leveraging this is as the number continue to come down, the power consumption on these boxes will continue to come down. It will utilize a lot less power. Whenever we talk to customer, 3 things always happen: space, cooling, and power. So we are solving some of those logistic problems. And then let's zoom in. This is a J2C box. Can support up to 36 400 gig port non-blocking in a 2 RU chassis. I'd like to welcome everybody. When you have time today, if you go to my left all the way down, we have a showcase at the Experience Center. We are showing the good old J2, the existing J2C Plus, as well as talking about some of the future things that come out in the near future that we can do a non-blocking line rate of 800 gig. So with that, we turn over to Chris to talk about the cabling. This one, only touch this one. All right.
Thanks very much. My name is Chris Collins from Credo. Credo brings the interconnect to this picture. So my friends here talked about the software, the hardware boxes, but the other piece of this is how do we connect these things? And in a DDC chassis, not like a traditional router, there's no backplane. The backplane is essentially replaced by the purple cables you see in the picture up here. And one of the great things about this is the level of densification and the pace of the advancement that this type of architecture brings. So what you can see on the screen here, in only 2 years, we've gone from the system on the left, based on the J2 chipset, to 92 terabit router. Showed that here a couple of years ago, and we actually have the same mock-up over in the Experience Center today. This one uses the 400 gig AECs, and the power per 400 gig port, often how these routers are kind of evaluated, is about 100 watts. Last year, we upped the game, including this new Jericho 2C chipset. One of the big things here is the actual capacity went from about 96 terabits up to 350 terabits. At the same time, the power per 400 gig dropped in half to 50 watts. So you can see that in the same footprint, same 3 racks, we are 3.5 times the capacity and half the power per 400 gig port. This year, on the very far right, we're projecting in the future what's coming on would be a Jericho 3. And in this particular case, now we're further reducing the power per 400 gig port down to 35 watts. And one of the ways that we do that is with this brand new cable that's no longer a 400 gig active electrical cable. It's the world's first 1.6 terabit active electrical cable. So same footprint, still in 3 racks. Over the course of 2 years, we've increased the capacity 7x. And if you think about trying to do this in a traditional chassis-based router, it's virtually impossible. I mean, yes, you can plug a new line card in with a new ASIC on it, but if you don't have all of those traces already on your backplane, you just can't increase the capacity without ripping the whole system and replacing it. Here, adding new white boxes, you can really get the advantage quickly and basically as you need it. So the piece I alluded to on the last slide was this brand new 1.6 terabit active electrical cable. So what is an active electrical cable? It's a copper cable, but in the 2 ends of that cable, in this case, those are OSFP XD, standard form factor, Credo has put our retiming silicon. So in each end, there is a 1.6 terabit retimer, has 16 lanes of 112 gigabit per second, and facing the actual router to the outside world, it's a standard AUI interface. So this means it can communicate with any ASIC with 100 gig I/O out there. This cable is about 20 watts per end today, and you can get them up to 2.75 meters. The jackets are very thin, they're only 6.8 millimeters, and if you come over to the Experience Center, you can touch and feel one yourself. Very flexible, easy to cable manage, even in super high density like you saw in those pictures. Credo does all of the cable in-house, so our own silicon is inside at the end, and we have the cables manufactured and branded as part of our business. So recently, the active electrical cable has been brought under the OCP umbrella as part of the Interconnect work group, and we'd like to invite everyone to come over and take a look at the Experience Center or at the Credo booth to get a better look at these cables. Thanks very much to my fellow speakers. I think that's the end.